Hi everyone! Today we're going to be talking more about triangle congruence. Our objective for today is that students will be able to use the ASA, AAS, and HL postulates to test for and prove triangle congruence. Let's get started. Alright, so last class we talked about SSS, side, 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 and SAS, side, angle, side. Today we're going to be talking about a couple more postulates. So first off, let's start with angle, side, angle. So one way we can prove triangle's congruence with fewer parts is if we can prove that two angles and the included side of one triangle are congruent to two angles and the included side of another triangle. Alright, then we can say the triangles are congruent. So what this means, we have to be able to prove that one angle is congruent to another angle. So for example, if angle A is congruent to angle D, and then we can say that another angle right next to it, so let's say angle B, is congruent to angle E. So we have two angles right next to each other. Obviously, they have to be right next to each other. But then the side we have to prove congruent is the side that lies between them. Alright, so that would be the included side. So we have to say that the side between those two angles, the included side, is also congruent. So if we could say that angle A is congruent to D, angle B is congruent to E, and side AB is congruent to side DE, then by angle, side, angle, we can say that the two triangles are congruent. So then we can say triangle ABC is congruent to triangle DEF. Alright, so here's a sample ASA proof. Start with our given information. We know that SQ bisects RQT. Alright, so RQT would be this angle right here, and RST, this angle right here. Alright. So we know that it bisects. That is a given piece of information. It bisects those two angles. Our goal is to prove that the two triangles are congruent. So the first thing we can say is if we know that, oops, I wanted my eraser. So if we know that QS bisects both of those angles, then we can say that RQS is congruent to TQS. Alright, and the reason for that is because if QS bisects this angle, that is the definition of an angle bisector. It cuts the angle in half and makes both angles congruent to each other. So the reason that those two angles are congruent to each other would be definition of angle bisector. Alright, and then we also know that QS bisects this angle right here, so therefore we can say that RSQ is congruent to TSQ. Alright, and that's also by definition of an angle bisector. Alright, then we have two triangles that share a side. So anytime they share a side, that side is congruent to itself by reflexive property. Alright, so QS is congruent to QS by reflexive property, and that would be our reason. Then we can say that triangle QRS, so this triangle up here, is congruent to triangle QTS, this triangle right here, because we have an angle, and the included side. We have an angle, and the included side. So by angle, side, angle, side, angle, these two triangles are congruent. So our reason for statement number 5 is angle, side, angle. Alright, proof number 3. Now we're not given any statements or reasons, so we've got to fill this one in ourselves. So always start with the given information. So we're given that angle BAC is congruent to angle DEC. That's a given piece of information, and then we want to mark it on our diagram. So BAC is this angle, and DEC would be this angle. Those are congruent. Now we're also given that C is the midpoint, and I'm going to abbreviate because I'm going to run out of room here, of AE, and that is a given piece of information. Alright, so we know C is the midpoint of AE. Now, we can conclude something based on this information. So if we know that C is the midpoint of AE, then we know that AC has to be congruent to CE by definition of a midpoint. So that's something else we can conclude from the diagram. So we want to write that AC is congruent to CE. And our reason is because that is the definition of a midpoint. All right. Then, just by looking at our diagram, we know that we have some vertical angles here. So we can say that this angle is congruent to this angle because they are vertical angles. So by the vertical angles theorem. All right, so let's say that angle BCA is congruent to angle DCE because they're vertical angles. All right, or the vertical angles theorem. Then, now we look at our diagram, we've marked it up, we've got angle, angle, and the included side. Angle, angle, and the included side. So therefore, we can say that these two triangles are congruent by angle, side, angle. So we can say that triangle ABC is congruent to triangle EDC by angle, side, angle. All right, that was a bad A. There we go. Angle, side, angle. If you have any questions on this, call me over so I can help you. Otherwise, let's move on to another postulate. All right, another postulate we're going to talk about is angle, angle, side. So if we have two angles and a non-included side of one triangle, and those are congruent to two angles and a non-included side of another triangle, then the triangles are congruent. And just so we know, non-included means a side opposite of either one of the angles. All right, so our example here, if we have that angle A is congruent to angle D, all right, so we've got one angle. Angle A is congruent to angle D. And then we can also say that the angle right next to it has to be right next to it. Angle B is congruent to angle E. And then we're also given one of the sides that are non-adjacent. So if we're given that BD is congruent to EF. Oops, not angle, side. Side BD is congruent to side EF. So if we're given two angles and one non-included side, you could have also said side AC is congruent to DF. All right, either side would have worked here. Then we can say that the two triangles are congruent. So then we can say triangle ABC is congruent to triangle DEF. So we have to be able, in order to use angle, angle, side, has to be two angles and a non-included side. So it has to be either side other than the one that's between the two angles. All right, let's do number 4. I know it's an even, but we're going to do it anyway. So a sample AAS proof. Start with our given information that YZ bisects angle WYX. So that's this angle right here. All right, YZ bisects that angle. All right, let me draw that a little better. So we know that it bisects that angle. We're going to write that as a given piece of information. So YZ bisects angle WYX. And that is given. We always start with our given information. Then we know that angle YWZ is congruent to angle YXZ. And this is also another piece of given information. We want to mark it on our diagram. So YWZ would be this angle right here, is congruent to YXZ, which would be this angle right here. We marked it on our diagram. Now, our goal is to prove these triangles congruent, and we want to use AAS in this proof. So using our given information, what can we conclude? So, nothing really we can conclude from the two-angle statement number 2, that the two angles are congruent. Awesome, we've got one angle. Then, YZ bisects WYX. All right, so we know if YZ bisects this angle, all right, that means that this angle is going to be congruent to this angle because that is the definition of an angle bisector. It cuts the angle in half. All right, so we can say that angle W, oops, that doesn't look like a W, W, Y, Z is congruent to angle X, Y, Z because of the definition of an angle bisector. Oops. All right. Then we know that there's two triangles here and they share a side, they share YZ, so we can say that YZ is congruent to itself by the reflexive property. Anytime we have two triangles that share a side, we're most likely always going to use that piece of information. So we can say that YZ is congruent to itself by the reflexive property. Now we've got angle, angle, and a non-included side. Angle, angle, and a non-included side. So therefore we can say that these two triangles are congruent by angle, angle, side. All right, and then we would just write our congruency statement right here, that WYZ is congruent to triangle XYZ, and it's because of AAS. All right, number 5, always start with the given information. All right, so we're given that angle ABC is congruent to angle CED. So we write it in our proof as a statement. Our reason is that it's given, all right? And then we mark it up on our diagram. So angle ABC would be this angle right here is congruent to CED, all right? Then we're also given that AB is parallel to CE. This is given. And we want to mark it on our diagram. So this line is congruent or parallel to this line, all right? That the little arrows mean parallel. Then we're given that C is the midpoint, and I'm abbreviating because I'm going to run out of room, midpoint of AD. And this is given information. All right, so C is the midpoint. Then we want to ask ourselves, what can we conclude based on this information? So if we know that C is the midpoint of AD, then we can say that AC is congruent to CD because of definition of a midpoint. All right, so we say that AC is congruent to CD by definition of a midpoint. Then we want to use our other information, knowing that we have two parallel lines. All right, we know that these two lines are parallel. And then what if we said this was our transversal? Then we can conclude that these two angles would be congruent because they're corresponding angles, all right? So always identify what are your two parallel lines and what would be your transversal. In this case, AD is the only one that cuts through both of them, all right? So that's the only line that goes through both triangles, so that would have to be our transversal. So we would say that angle BAC is congruent to angle ECD because of corresponding angles, all right? They are corresponding angles. Then we can say that the two triangles are congruent because we've got an angle, and a non-included side. We've got an angle, and a non-included side. So by AAS, these two triangles are congruent. So we write out our congruency statement, and our reason is angle, side. All right, I want you guys to try number 7. Go ahead and try to fill in this proof on your own. See if you can do it. When you come back, I'll have the answer written on your screen and we'll go through it together. So remember, start with your given information and go from there. All right, give this one a shot. When you come back, we'll go through it together. So go ahead and pause your video now. All right, here's the answers to number 7. Let's go through it together. So start with your given information that LG is parallel to JM. Two little arrows indicate that, and we write given. H is the midpoint of LM, so H is the midpoint of LM. Given information. Then from this piece of information, if we know that H is the midpoint, we can say that LH is congruent to HM because of definition of a midpoint. Then, if we go off of the information that LG is parallel to JM, and if this is our transversal, then we can say that angle G is congruent to angle J by alternate interior angles. Now, if you would have said that LM was your transversal, which you could have done, then we would have proved this angle is congruent to this angle by alternate interior. Then we would have been using angle side angle, which works, but we would have just needed to say angle side angle, not angle angle side, all right? And our goal here is to use angle angle side. So that's why we said that GJ was our transversal and that angle G was congruent to angle J by alternate interior angles theorem. Then we say that angle LHG is congruent to angle MHJ because of vertical angles theorem, they're vertical angles. Then by angle angle side, because we have two angles and a non-included side, two angles and a non-included side, these two triangles are congruent by angle angle side. All right, if you have any questions on that, call me over so I can help you. Otherwise, let's move on. All right, the last triangle congruence theorem we're going to talk about, and this one's a theorem, not a postulate, all right, is hypotenuse leg, or HL. All right, so the hypotenuse leg theorem, or HL theorem, tells us this is specifically for right triangles. All right, so if the hypotenuse and a leg of one right triangle is congruent to the hypotenuse and the leg of another right triangle, then the triangles are congruent. All right, so first thing I want to explain to you guys is what is the hypotenuse and what is the leg. So if we have, oops, I want a pen. If we have a right triangle, all right, this is our right triangle. The hypotenuse of, oops, I wanted a highlighter. The hypotenuse of a right triangle is the side opposite the right angle. All right, so if this is our right angle, the side opposite it would be this side right here. All right, so basically what we do is we look at our right angle and go to the side opposite that. So this side would be our hypotenuse. Then the leg of a right triangle, legs of a right triangle are the sides adjacent to the right angle. So we've got our right angle, the sides adjacent to it or right next to it would be these right here. So those two sides are our legs. All right, so hypotenuse is always the side opposite the right angle. The legs are always the side adjacent to the right angle or right next to the right angle. Okay, so the HL theorem, hypotenuse leg theorem, tells us that if the hypotenuse and one of the legs are congruent, then the triangles are congruent. So for example, here we're given that the hypotenuse, we're given that BC is congruent to EF. Those are both the hypotenuses because they're opposite the right angle. So if BC is congruent to EF, and then one of the legs, so here we're given that ED, is congruent to BA, but you could have been given that DF is congruent to AC, all right? Either way, it doesn't matter here. So we write that in. We say that AB is congruent to DE. That's one of our legs. Then we can say that these two right triangles are congruent. So then we can say that triangle ABC is congruent to triangle DEF. All right, so the hypotenuse leg theorem only works for right triangles. All right, so example HL proof. Our given information is that triangle LMP and MNP are right triangles. We have to be given that they're right triangles, otherwise we can't use the HL theorem. So, given information. And we're also given that ML is congruent to MN. All right, so this is given information, and we want to mark it on our diagram. Now our goal is to prove that LMP is congruent to triangle MNP. All right, so we know that these are both right triangles, and we know that we have the hypotenuse is congruent. So we need to prove that one of the legs is congruent. And because they share this side, they share MP, we know that MP is congruent to itself by reflexive property. All right, and MP is a leg in both of the triangles. So we've proved that one of the legs are congruent and the hypotenuses are congruent and that these are right triangles. So we can say that triangle LMP is congruent to triangle MNP by the HL theorem. All right, and we're going to do number 2 together. I know it's an even, but we've got to do it. All right, so triangle WVX and triangle YZX are right triangles. So that's our first piece of given information. Let's write it down. Triangle WVX and triangle YZX are right triangles. Given information. All right, we need to know that they're right triangles. Now, we can assume that there's our right angles. Then WV is congruent to YZ. That's another piece of given information. So we write it down. We marked it on our diagram. We wrote it in our proof. Then we're also given that X is the midpoint of WY. Given information. So X is the midpoint of WY. Now, from that piece of information, if X is the midpoint of WY, we know that WX is congruent to XY. And we know that because that is the definition of a midpoint. So that's another statement we can make, that WX is congruent to XY. And we know this because we're given that X is the midpoint, and that is the definition of a midpoint. All right, now we've proved that one of the legs, this is a leg and a leg, we've proved that one of the legs are congruent, and we know that opposite the right angle, this is our hypotenuse. Opposite the right angle, this is also our hypotenuse. So we've proved that the hypotenuse and a leg are congruent in both triangles. So we can say that these two triangles are congruent by the HL theorem. And we're done. All right, last but not least, I wanted to share a little video with you guys. I found it on YouTube. It's called Why ASA Does Not Prove Triangle Congruence, and it's by Mashup Math, and there's the link. I couldn't figure out how to embed it in this video, so if you're curious as to why SSA does not prove triangle congruence, why doesn't it work, you can either type in this link or just search Why SSA Does Not Prove Triangle Congruence by Mashup Math on YouTube. And this quick little video does a great job at explaining why SSA does not work, all right? And it has a donkey in it, and I thought it was funny, all right? So if you're curious as to why it doesn't work, go and watch this video, all right? Otherwise, hope you learned a thing or two about ASA, AAS, and HL today. If you have any questions, call me over so I can help you. Otherwise, look to the board to see what to do next, and I hope that you have a great day. Bye!